How is the entropy of mixing calculated for a mixture? Imagine you have two different gases in separate containers. When you open the valve between them, they mix on their own. Why does this happen? Because mixing increases the disorder of the system. That increase is what we call the entropy of mixing. Now, how do we actually calculate this change in disorder? That's what we're here to find out. The entropy of mixing measures how much more random or disorganized the system becomes when different substances combine without any chemical reactions. It's a way to see how natural processes tend to move toward more chaos or disorder. To figure out the exact amount of this increase, we use a specific formula that works well for ideal mixtures. These are mixtures where the components don't react chemically and behave predictably. The key idea is to look at the mole fractions of each component in the mixture. Mole fraction is just the ratio of moles of a particular substance to the total moles in the mixture. The formula for the change in entropy due to mixing is the change in entropy equals negative the total number of moles times the ideal gas constant times the sum of each component's mole fraction times the natural logarithm of that mole fraction. Mathematically, it looks like this. The change in entropy equals negative n times r times the sum over all components of Xi times the natural logarithm of Xi. Here, n is the total moles in the mixture, r is the ideal gas constant, and Xi is the mole fraction of each component. Each term Xi lane shows how much each component contributes to the overall increase in disorder. Since mole fractions are always between 0 and 1, their natural logarithms are negative. That makes each Xi lane Xi term negative. But because of the negative sign in front of the entire sum, the total change in entropy ends up being positive. This confirms that mixing always increases disorder in ideal systems. For example, if you have a mixture of two gases, like gas A and gas B, the formula simplifies too. The change in entropy equals negative the total moles times R times the sum of XA lane XA plus XB lane XB. This simple version helps us understand how the proportions of each gas influence the increase in entropy. The calculation can also be linked to how gases expand when mixed. When gases are allowed to expand into a larger volume, their entropy increases because they have more space to occupy. This expansion is directly related to the entropy of mixing, showing why mixing is spontaneous and doesn't need energy input. In practical terms, knowing how to calculate the entropy of mixing helps us understand why gases and liquids tend to mix naturally. It also impacts how we design chemical processes, predict phase changes, and understand solution behaviors. It's a fundamental concept that connects the microscopic arrangement of particles to the larger thermodynamic picture. So, to find the entropy of mixing, first determine the mole fractions of each component in your mixture. Then, plug those values into the formula. Negative total moles times R times the sum of each mole fraction times its natural logarithm. The result tells you how much more disordered your system becomes when the components combine. This increase in entropy explains why mixing happens spontaneously and is an essential part of understanding thermodynamics.